All right, thanks everyone. Thanks everyone. So my name is Amod. I'm an engineer. I'll be talking about quantization. This is something that I got interested in because of a particular, thing that caught my eye. That a Llama 7 billion parameters model. Somebody was actually able to run it on a Raspberry Pi. Okay, for those of you who may not be familiar with things like this, 7 billion parameters, each parameter being stored as 2 bytes, translates into essentially 14 GB of memory. And all of this was running on a 4 GB RAM. So which is why I thought, I actually got curious about it. And I thought it would be useful to share with everyone. I will try to keep the conversation as easygoing as possible. There is a bunch of technical stuff, but the idea is to leave you guys with intuition, with enough link to follow up on your own. This is not a substitute for paper reading. That's something that all of you will have to do if you want to go deeper into this. And most likely I'll be able to cover only half of the talk. We'll see how much we are actually able to gain ground. But this is a very important technique going forward. As models become more and more complex, they will become larger. And it's for us to be able to deploy models on very small devices, very constrained devices like our watch, our televisions, even our laptops for that matter. We will need to learn about these techniques. So the real question is before we get to everything, we need to understand what's inside a model. How many of you can read this right now? No, not legibility. I mean, how many of you immediately know what this is about? Okay. So it's very important. This is not a test. The idea is that a lot of what I'll be talking about would not make sense at all if this is not clear. So I'm just going to go through this very briefly. Hopefully it sticks. This is the essence of a neural network. You've got a bunch of inputs coming in. This is something that does a weighted sum of it along with a bias. There's an activation function that actually makes this unit learn nonlinear functions. So the essence of all of this is this thing is able to learn any function in the world. Okay, that's the essence of, so neural networks are called universal approximators because they can learn any function. And we represent something like this. This is your input layer. These are your hidden layers. That's your output layer. These are terms that I would be using, which is why I'm introducing all of this. Sorry if it is repetitive. 3-dimensional input, 2-dimensional output. We've got hidden layers of 4 dimensions. We can imagine this as 3 dimension getting projected onto 4 dimensions, right? And then ultimately getting projected back to 2 dimensions. All of this is essentially standard basics of neural nets. Each one of the numbers that I listed down earlier, each one of these numbers, the weight, the bias, these are what constitute as parameters. All right, and we typically write a network like the output is a product of the input matrix. We can represent this as a matrix of numbers, and weight matrix, which represents all of these intermediate layers. So it's a product of 2 matrix. So that's all neural networks are about: multiplication and addition of lots and lots of numbers. All right. We'll jump straight to vision transformers. How many of you actually, I should ask that question. How many of you have actually written a model from scratch in the past, no matter how simple? Okay. So the idea is that I showed you this diagram. Essentially, each layer in this diagram, this layer, this layer, this layer, is just one of those graphs of dots that you saw earlier. Okay. And each one of them can be represented with just these 2 matrices. A weight matrix, which represents that hidden layer which was transforming, and a bias, right? So just each one of these layers can be represented as this. This is what we refer to as parameters of a model. Okay. In fact, just to quickly, okay, this works. So let me show you very quickly a super simple model. So I'm going to use PyTorch. What I'm doing right now is I'm actually creating a model. The first layer of that model expects a 100-dimensional input and outputs a 200-dimensional output. We call this a linear network. We call this as a linear layer. And I've made a mistake actually, sorry. And we'll gate this with a ReLU. You don't have to think about what that is. The next layer takes in the 200-dimensional pass from the previous layer and outputs a 150-dimensional output. And we'll end with a softmax. Okay. So now what we'll do is, I'm just showing you when you receive these model files, what you are actually receiving. Let's call it mymodel.pth. How many of you have seen a PTH file? Right? Anybody who's loaded a model, correct? So you can see, who can tell me what is the size of this file going to be? 100 times 200 plus 200 times 150, that many number of parameters we'll see, which comes up to about 2020K, 30K, 50K. Oh, is some mistake that I've done? Yeah, sorry, 200K. What is, so 2,000, 20,000 plus 30,000, 50,000 times 4 bytes per parameter. That is what it essentially the file represents. Okay. I have a script. It shows you what I had created. You can see this as, you can read this as 100 times 200. Okay. And you can see that total parameters 50K, size this. Now this is important. Each one of these parameters I can represent these as 4 bytes, 2 bytes, 1 byte. And obviously the total size of the model actually changes. Now let me show you the model that we'll be working with in this demo. It's what is known as a vision transformer. Okay, just like you've got the transformers for your LLMs, you've got vision transformers for images. Okay, let's look at what that is made of. This one is 86 million parameters at 4 bytes, 330 MB, 2 bytes, 165 MB, and so forward. Right? This is what I'm actually representing here. 86 million parameters, which will effectively translate into 18 billion floating point operations effectively to actually convert one image and process one image. Okay, and the papers are in those QR codes. These are the sizes. Okay. Why reduce the model size? Why are we talking about this reducing the model size from 320 MB to 80 MB or 40 MB? Yet to understand this, we need to understand GPUs and CPUs. All right. I told you neural networks are all about very large matrix multiplications. All of you would be familiar with matrix multiplications get done very fast on GPUs, and CPUs, it ends up actually working a lot more slowly. And one reason that is given is a lot of cores. But the real reason is that, I mean, a very crucial gating criteria is the memory bandwidth. These processors need to be fed, be able to feed that much amount of data. Otherwise, they will be starving. In fact, your average CPU core is actually, starving for majority of the time when we use our laptops usually. Okay. The memory bandwidth of a GPU is 1 to 3 terabytes per second. This one is 150 to 400 gigabytes per second. Okay, that's the kind of difference that we see, which is why GPUs can actually feed those processors so much. Okay, this is a fascinating topic. We should probably talk about it in detail at some point in time. But for the timing, we'll actually proceed with this. The point is that we need to be able to deploy that 320 MB model file onto this memory so that these processes can be fed. Because if we are not doing this, it will have to fetch it from the main RAM, which is actually going to be quite slow. PCI 5 is 4 gigabyte per second per lane. So at 16 lanes, that would be 80 gigabytes per second. So this is actually going to be a pretty slow bus. Model has to be deployed here. Okay, if it is not deployed here, your inferences are going to run super slow. Okay, so that's why memory reduction is important. But more than just memory reduction, notice what happens. Your GPUs are designed in a way that your floating point 16, which is a 2-byte floating representation, it can do 312 teraflops on a tensor core. Int 8 can do 624 teraops, because obviously there's no floating point. So this is not flops, this is ops. So 624 teraops. And if we were doing int 4, yani 4-bit integer representation, for some reason, by some magic, we were able to convert every number in that matrix into a 4-bit representation. We could do 1.2 peta ops. That is the kind of speed that we would actually be able to do. More than that, it would actually be hitting the cache very, very, very high cache hit ratio, which essentially keeps it well fed. Okay. So with that, let's quantize. Any questions till now? Yeah. Sorry, what? Oh, A100, H100. That's just, A100 is NVIDIA's older model. H100 is the newer one. You can see that each one of them is a jump. Fascinating topic on its own in terms of what kind of engineering actually goes behind to make such jumps happen, but not something that we can go deep into it today. But we should definitely talk about it at some point in time. All right, so we'll start with a super simple demo. Remember that 4-byte representation of a weight, a number in that big matrix goes into something like this. Okay. And the way it works is, the way floating point representation works is that you've got a 1 byte of sign, plus or minus, 8 bits of exponent. So if this exponent, if its value is 10, to simplify, then 2 to the power 10 times this fractional bit. This fractional bit is just like you've got decimal fractions, you've got binary fractions. 2 raised to minus 1 is 0.5. 0.25, 0.125. So with every bit, we are actually getting more and more precise. Okay, that's how things happen, which is why to represent real numbers in floating point, you need lots of bits on the fractional side. We refer to that as precision. So floating point 32 has lots of precision. Floating point 16 will have lesser precision, and so on and so forth. Okay, as you can see, floating point 16 has only 10 bits of fractional precision. All right. What we are going to do is we are going to simulate. We are going to simulate the effect of lesser precision on a model evaluation. And we'll do that by making the fractional bits disappear. We are going to set that to 0. This process is called truncation. All right. So with that, let me do a demo. The repo of this is actually online. You guys can do this on your own as well. All right. Yeah. So if you heard about transformers, you know that transformers work on attention, right? Right. So what transformers do is they look at an input and actually see what corresponds to what, like what is related to what. In this, so we are essentially, this is a visualization of what the transformer is seeing. So here, this model is actually looking at that original image and calling this out as an Egyptian cat with a 62.3% probability. This is the original model. This is the reduced precision model. Reduced precision currently will control how many bits of precision we are gathering. 23 bits is where, so full at 23 bits of precision we are using right now. So response is exactly the same right now. Let me reduce this to 10 bits. Almost the same. 13 bits of redundancy. Let's see the classification probability, almost the same, 62.3, 62.28. Wow. Let's reduce this to 5. Let's see what happens. Okay. 62.3, 62%. Wow. That much redundancy was sitting in that weight. Let's reduce that to 3 or 2. Here it started breaking a little. So transformer is now not able to, sort of associate the different parts of the image as accurately. And this has dropped as well, 62.3, 19.79. Remember, this happened at 2 bits of precision. Let's marginally increase this to 3. It's a demo you can run on your own laptop. Okay, at 3, it is something slightly better. At 4, a lot better, almost at the original. For the sake of it, let's just do 0. Yeah, all over the place, right? Okay, this is a demo that you guys can run on your own laptop. The instruction is there on the in that repo. All right. So the important thing is that we were able to eliminate huge number of fractional bits without any effect. Okay, and this is what quantization as a technique exploits. It actually finds those redundancies in your data and actually compresses them out. All right, and those are the techniques that we'll be studying about it today. So what we are clear on till now is that there's a lot of redundancy that exists inside the model usually, and if we were to compress it out, then we can save a lot of memory. And our CPU can get sped up because of the smaller bit width of each data. All right. This is what is known as a uniform quantization. There's a different quantization techniques. We will cover only the basics. I don't think we'll have time, but I will share this PPT and you guys at your own leisure can go through the advanced techniques. This we are referring to as the int8 technique. So what we are doing is, remember, floating point is going to come as a real number, some number on the real number line, correct? int8, 8 bits. How many values? 256, right? So minus 127 to, minus 127 to 127. That is the range that will represent this at. Well, the way we actually do this mapping is essentially we project this onto this. If this is my starting range of the weights and this is my ending range of the weights, my starting range I map onto minus 127, my ending range I map onto this. 0 gets mapped onto 0, and every number ends up getting projected on this, int8 line. Int8 line will essentially have 256 or 255 buckets, right? So each one of those buckets is getting projected at. Let's say that we have this number 2 on the int2 line. A range of values are going to map down to this. This is why we call it as quantization. There's lots of information that is happening. So if we were to actually do a reverse quantization operator, we are never going to recover the number that was here. We can only get like the one of those numbers in that range. That's called the resolution. All right. And this range of alpha beta we refer to as clipping. The scaling factor, S is the scaling factor. I'm sharing a technique, a variant of this technique, which is called essentially the abs max technique. This is the technique that gets used in Llama. That original tweet that I had shown, which was about compressing Llama models to int4. Essentially, int4 means that your niche wala line is 4 bits. So 16 possible combinations, and your scaling factor would be accordingly. All right. So this is your quantization number, which means that given a number R by S is where it will actually end up getting projected at, and the reverse quantization operator. All right. This is exactly the thing. If you look up llama.cpp, the project that I was talking about earlier, this is what happens. what is happening is, if you look at, I'm just sharing all of these things so that you understand that this is nothing in Hava. This is actually pretty real. There's something that actually gets used in all of these projects. You would see that we calculate the abs max approach, max of alpha and beta. All right. What that does is, the reason why we use max of this is that if it is -1 to 3, your range, your actual clipping range should be 3 to -3 for it to be uniformly mapped. Correct? So this becomes your scaling factor. And then we apply this scaling factor to, these are your actually two floating point numbers, which you are essentially calculating the mapping for. V0 and V1 now become int4 numbers. These are 4-bit numbers, which you can validate by this assertion. 4-bit numbers means that their value is guaranteed to be less than 16. All right. And these, the llama folks, the llama.cpp folks end up packing it into one 8-bit number, because 2 4-bit numbers they pack it into one. All right. So pretty real. int4. Any confusion? All right. Now, remember this piece. The important takeaways here is the clipping range getting mapped onto, whatever it is, int8 or int4 that you want to map it onto. How the distribution of weights in your original range, your clipping range alpha beta that we had decided. Okay. These are your alpha and beta. In practice, it will map onto, say, for example, -1.2 to 1.2 or 1.5. Okay, that becomes your range. And all the weights inside that matrix have this sort of a distribution. What the quantization is actually doing is drawing these grids on it. Right? And each number in a certain range ends up getting mapped onto one particular bucket. All right? This is all good. This is fairly straightforward based on the earlier picture, I assume. Let's talk about the outlier problem. What happens if your distribution actually looks something like this? It's a very Falloward distribution. Okay, so your clipping range, your min and max are so far spread out that if you were to use it, majority of your numbers end up mapping onto just one single bucket, and they'll end up taking only one single value, right? And just like in life, diversity is important here. Otherwise, your weight matrix is essentially going to be a dead one, because all the entries have the same value. Okay. All of the rest of the things about all of the advanced concepts are about figuring out this outlier problem. All right. So our basics are covered. How are we doing on time? We have 10 more minutes for the 30 minutes to. Okay, cool. So then we can at least get into one useful, more advanced version of this. In such an outlier problem, there are different kind of techniques you can take. One of them is clip, snip, snip. Say, for example, we were to figure out through some means, we were to figure out that all the weights below this don't really have an effect on the end output, on the end inference. Okay. In that case, we can set them to 0, set that to 0. And all of this, we project it onto the full 8-bit or 4-bit range, and thus getting more granularity within this distribution. Correct? So this is one approach. If we were to do this, and this gets used in enough number of cases, it's important to figure out the sensitivity of the ones that we are eliminating. Standard approaches exist, something called Hessian, etc. I'll not, without getting into some of the mathematics behind these multiplications, or I don't think it's useful, but there are some techniques that exist through which you can figure out how sensitive the model is going to be to this. Okay. The second one is to reduce granularity to per tensor than the whole model. Now this set of weights, we can imagine this as doing it for the whole model. What is the minimum weight that exists in my whole model file, and what is my maximum? This will obviously have a much larger range, I suppose. Correct? If we were to look at the this visual transformer model, you can see that some of these matrices, I'm using the word matrix, technically they are tensors, but effectively the same thing for this discussion. You can see that some of these have -1 to 1, while some of these have, notice this one, minimum is 0.06, max is 0.5. So there is some variation, right? Between different layers. Different layers have different distributions of these weights. So one of the things that we can do is, instead of doing this alpha beta thing for the whole model, we actually apply it on a per layer basis, right? So that is one approach that we could take. That will make sure that we get a nicer model like this. Another approach could be that we could reduce the granularity even further to per row column of that matrix. Remember, I had talked about that there's a input can be represented as a matrix, the hidden layers can be represented as a matrix, and we multiply the two to get the output. Okay. Instead of that whole matrix being treated, the second option is about we evaluate the quantization on a per matrix basis. The third option is on a per row and column basis. We are actually doing it. Okay. No, this is the rows and columns usually represent. So one column, for example, one row could mean one feature, one hidden feature inside the model. Right. So they are very abstract domain representations that, as an example, let's say, let me ask you, king minus man plus woman is equal to what? Anybody? Queen, right? So there's a hidden representation that we have where, king represents some royalty axis and we've got a gender axis, right? And the king is a combination of royalty plus the gender being a man, right? And when you do the minus man plus woman, you end up getting into a queen. That abstract space of features is essentially what you're referring to. Make sense? Okay. So the third one is reducing granularity to row and column of the tensor. Fourth one is getting into non-uniform distribution. Remember that when we were doing that int 8 example, it was a uniform projection. We took that top line, we uniformly projected it out onto the bottom line. Another one is non-uniform, where for example, you could have a logarithmic distribution. Far more complicated, rarely used in practice. In practice, what people end up getting into is that take uniform distributions, take uniform techniques, and figure out the slice of the distribution where it can be applied. And we use a bunch of them. For example, per row, per column, that sort of a thing, instead of getting into non-uniform quantization. Okay. LLM.int8. How many here have heard of this? Okay, a few. So this is something which is one of the techniques that actually uses the per row per column thing. All right. So instead of quantizing this whole matrix and that as another quantization of a matrix and multiplying them, what this does is vector quantization, which is essentially rows and columns. We quantize individual vectors and we actually multiply them. All right, which means that when we were evaluating that alpha beta, we had to look only at this range of values, which is great for us because the variation scope is lesser. It's a smaller set of values. Hopefully the variation is going to be much lesser. All right. And this is what, these guys had actually been using, and it actually gave amazing results. It actually allowed them to scale to about 2.7 billion parameters. But then an interesting thing started happening. This paper is by Detmers. That QR code actually links you to that paper. What actually started actually happening was that they started discovering outlier features, which means that we had quantized this row, but on this column, we saw particularly high values. Okay, not just that, our model had become so dependent on these that the slightest change on any value of this immediately drops your accuracy by 20%. These are the outlier features, and it's a very emergent phenomenon that happens as you actually, when you start going beyond this 2.7b number. Okay, and this cannot actually be quantized in this because we've already quantized this. Okay, and matrix multiplication works like what? You multiply a row and a column to get a value. You do not take a column and multiply it with a row, correct? Okay, so it actually became very tricky. Okay, so in fact, they actually called it out that outlier features. These are called outlier features. Okay, so that in that royalty and gender example, this would be probably a royalty axis. Okay. Outlier features are probabilistic in nature in smaller models. They may happen, they may not happen. In larger models, it's a guarantee. And they will, when they happen with very high sensitivity. It's almost like a guarantee. Okay. So which is why they had to come up with a different technique, which what it did was actually pulled out those outliers through a certain mathematical technique, which we'll not get into. It's actually not too difficult if you know linear algebra, but I think this is a simpler session. So they pulled out the outliers the yellow ones. The rest of the ones they multiply, they quantize using 8-bit, and the more sensitive ones they quantized using 16-bit and then smash them together. Okay, so for those of you who have a linear algebra background, you guys can go through that paper. Very interesting paper. Okay, the same problem is dealt with by another technique called smooth quant in a very different way. We don't have time for it. Just letting you guys know about it. It deals with exactly the same problem in a very different way. So fascinating ensemble of techniques that actually exist around quantization. All of them oriented to reduce the per weight size. The lighter it is, the better we are, because our memory size reduces and our computation is that much faster. That is the talk. The talk is available on on this link is the repo. The talk is available. Any corrections to this where I've made a mistake, you can actually just raise a GitHub issue and let me know. Any questions?
Hi. So although this might be slightly deviating from the topic, but just on the lines of normalization, to some degree, does quantization help with generalization and model performance?
Does normalization help in?
Quantization.
Quantization help in what?
Model performance or robustness.
It helps more model performance in terms of speed, but quantization almost always will lead to a reduction in accuracy. How do we control for it is where the efficacy of the technique comes into the picture.
Yeah. The only reason I asked is, I think the idea behind normalization is probably similar, where you reduce some specificity leading to better
normalization is for different things. I want to be very clear. Normalization actually essentially make sure that, for example, one of the features, if it is coming out too prominently, okay, it does not overwhelm the other features. So you are essentially normalizing it out effectively. Okay. So.
I think it's similar, maybe if you could add to what Amod said, the similar sort of idea, which is removing weights of certain nodes, for example, right?
Pruning.
Yeah, essentially called pruning, right? Which used to be very effective, but in today's world, it might be like slightly more trickier with transformers.
So yeah, so how does quantization or model which is quantized compare to a model which is actually trained on a FP8 or FP16? So
that's a good question. Actually, there is a technique called sorry, I logged out of the there is something known as quantization aware training. In general, during the training, you do not want everything to be quantized because of the simple reason that your gradient calculation needs to have a certain precision, because you are doing stochastic gradient descent, right? You are trying to figure out where the lowest level actually is, where my minima is, correct? That requires numerical precision. So you do not want to significantly reduce your bit width during training. But there's something called quantization aware training, where your training is actually happening in single precision like FP32 or something like that. But it is trying to adjust the weights in a quantized way. So your back propagation is actually happening on in single precision FP32, but you're still trying to adjust the weights of int 8. So that thing exists, but in general, you would not reduce the precision during training. I have not gone through the mechanics of that. But does it specifically, talk about fine tuning, or is it about quantization? Then maybe I have not gone through that paper, so I cannot comment on that.
Hi, thank you for that. That was amazing. You talked about the smooth quant and the one before that, the .int8,
Yeah.
where like you're able to find specific features which have an outsized impact on the output value, right? So when you're talking about model explainability, which like a lot of like the cutting edge research is happening, that is a pretty specific area of research, like identifying particular neurons in the entire network,
Yeah.
which have an outsized impact.
Yeah.
So am I right in understanding that the only way to kind of get to that is to like quantize and then go on training, and then at a certain point these outliers will reveal themselves, or is there like any other method to like find?
So the methods exist at all phases during the process, during the training process. Okay, you can figure out essentially how much your output varies based on that particular layer, a perturbation in that layer. To what degree does it actually lead to a large change in the output? So there are certain techniques that actually exist. Hessian, like I said, is actually one of them. The double derivative sort of a function, double derivative of that function.
Yeah.
Those sort of techniques exist. In general, in the int8 paper, what they talked about was these outlier features actually start showing up only beyond a certain scale with high degree of predictability. In the smaller models, it's a probabilistic thing. They may show up, they may not show up.
Got it. And one more, the speculative question, but OpenAI or like any of these large language models, they release like 6 billion model, then 65 billion, then like 130 billion, like that.
Yeah.
Is that a quantized model of the bigger one, or they're completely separate?
Releasing F16.
Okay.
So almost all of them end up releasing 16-bit models.
I see.
Which tells you that the number of parameters represents the complexity of the model.
Yeah, got it.
Richness of the model in some way, correct? It's much better to evaluate, instead of just directly using just Llama, instead of using a 7B model, end up using a 65B model in a quantized way. Does that actually give me a better output? But it needs to be evaluated. In general, if you quantize well, quantization at a higher number of parameters is going to be better.
Yeah, got it. Thank you.
One of the techniques on the input itself, right? Like you had a matrix. So if I link it to how they were able to run on a Raspberry Pi, if you have to keep finding out the alpha beta at every layer, which is dependent on the input.
Okay, so there are multiple granularities at which you can approach. For example, you can apply int4 only on the weights and not on activation. Activation, essentially input comes in, right? The weights and biases essentially get applied on it, and then output happens, which then feeds the next layer. So this output becomes the input for the next layer, right? You can choose to quantize only the weights, and that alone has been sufficient for such a massive number of. So in the Llama example, scenario, for example, if I understand correctly, they are quantizing only the weights and not the sort of activations. Okay, so there are some other ones, smooth quant, for example, smooth quant and int8, both of them end up attacking both the activation as well as the weight.
Do you know any other techniques? Like I know ONNX with static and dynamic quantization on SBERT model. So like any other libraries that are known for this quantization on the model, like or like people just generally do it like writing the code itself. Like
there are plenty of them. I think smooth quant folks have actually put out an integration with fast transformer. Or something like that. So a whole bunch of these folks have actually released different libraries which you can just integrate.
Yeah, I think SBERT has already, SBERT with ONNX had already.
I mostly go through papers and less about libraries because I like to understand the mechanics. So quite likely what you're saying is true, but I cannot validate it.
Hello. First of all, thank you for an amazing session. It was very interesting. My question is, when we are reducing the dimensionality of weights, basically, not dimensionality, but we are quantizing. Another way could be actually trying to reduce the dimensionality of the weight matrix.
Yes.
So can we use something like PCA here? Something like PCA here.
PCA, yeah. So maybe not PCA, but there are. So one of the reasons why we can do away with so many bits and everything still works is because DNS in general are significantly over parameterized. Okay, which means that there is a lot of leeway. One of the questions that I didn't get was that how can it happen that we did away with such a huge chunk of digits and everything still gets to almost the same accuracy? Okay, and I wish that I had time to walk through, but the reason is over parameterization. Over parameterization effectively also means that in your feature dimensions, there's a lot of your basis vectors are actually, if you understand that word, like there is a paper. It's linked in the resources section of the GitHub link, where what they discovered is in one extreme case, they found that amongst all of the model, 95% of information was redundant, and you could derive that information from 5% of the information. So from 5% of the weights, you could derive the rest of the model. Now, this is an extreme example, but that goes to show that there is certainly a lot of the dimensionality of a model is not fully independent, which means that you can essentially compress it significantly. For those of you who understand basis vectors, you can imagine that you can express a model far more in terms of the basis vector, which is what your PCA effectively actually tries to arrive at. It tries to bring that.
Understood. May I have a follow-up question? Not follow-up, but a secondary question. So as a practical user, if I want to quantize any model that I have, is there a robust way of evaluation? For example, you showed in the demo that after 4 bits, the accuracy dropped significantly.
Yeah.
But that was for one example. How would I know?
Yeah. So there are standard techniques, and I'll tell you about but something that some of the mathematicians have been working on. The standard technique is evaluating on perplexity. Okay, there's a bunch of standard measures depending upon the domain of the model, and you evaluate it on that. That's a little bit cumbersome, but so long as what you're working on has an existing test set, you can compare against that. A bunch of mathematicians have been actually working on this notion of using information theory of mathematics to try to evaluate at what point in time your mutual information actually starts coming down. Okay, so that's a very fascinating area to keep a track of. I have not included that paper in the resources section because I am not sure how many information theory followers are here, but that's an interesting area to track as well. Yeah, that's one of the. That's one of the things, but the one that I was talking about was something different. Yeah. Let me tell you the paper. Product composition is effectively what I was sharing with you earlier. That essentially what you do is you look at your all of the vectors in your dimension, and you start clustering the vectors that are closer together, and you represent that with one vector. So just like we were mapping those weights, instead of working with scalar weights, you are essentially clustering the vectors. Okay. Sorry, I am not able to, but I'll include that in the resources section as an redundant.
I have a very naive question about the memory bandwidth part, which is if the bottleneck is just the memory bandwidth, can't you build like a CPU with really high memory bandwidth?
Very, very good question. So I wish I was connected. You remember the diagram, right? So CPU is connected, every processing unit is connected with the memory band, whether it be CPU or GPU. through a certain number of pins. Okay, that essentially gives you the bus width. Okay, for every n number of bits, you need to put a controller usually. Okay, so for example, Z on the top end model, if I remember correctly, ends up putting up 8 such channels. Every channel ends up having a memory controller. So 8 channels, and every channel is 64 bits. So you end up getting 512 bits. Okay, 512 bits running at the DRAM running at 4800, DDR4 4800, 4.8 giga transfers per second times 512 by 8. It should come up to about 400 gigabytes per second, if my calculations are correct. Okay. So the point is that putting in these lanes, these pins, is costly. GPUs work on a very different principle because it's on the same die. They end up essentially using a technique called high bandwidth memory, HBM3, where you end up essentially vertically stacking these memory units, and you have pins actually dropping down to the substrate. Like I said, the GPU wala thing, you can, like, I can go on and on about the engineering matters, fascinating engineering. But for CPU to replicate it, it's much more costly.